We'll close out our discussion of nuclear physics, that is physics of the nucleus, by talking a little bit about binding energy, which is going to lead us to fission and fusion. So we get to talk a little bit about the practical applications of nuclear physics. All right, last time we talked about the nucleus and the sort of strange fact that all of these protons can be packed together um, without exploding away from each other. And now we want to talk a little bit about why that is. And the reason is that there's another fundamental force here, right? What are our four fundamental forces? Gravity, the Coulomb force, which is the force that's trying to make these protons move away from each other. But then we have two forces that act only on the quantum level. One is called the weak force, which is crucial to beta decay, and we're not going to really touch much on the weak force. But that fourth one is called the strong force, and this is what bonds nucleons together. It has a really short range, but it's extremely strong. Okay, so it only acts between particles within the nucleus. But it is strong enough to overcome what is going to be a pretty considerable Coulomb force here. So how much bigger is it than a Coulomb force? Well, if we think about how much energy it takes to overcome something, if we want to free an electron from its Coulomb attraction to a proton, it might take a few eV, electron volts, but it would take millions of electron volts to free a neutron or proton. So it's much stronger in its sense than the Coulomb force. So why does this matter? Well, when we start talking about nucleuses, that force is so strong that we have to start taking Einstein's equation between energy and mass into account. So an electron, we talked about before, has less energy when it's bound, right? Because it has a lot of potential energy when it's far away, and it loses that potential energy as it gets attracted to an atom. The same thing can be said of a nucleon. So a nucleon has less energy when it's bound in a nucleus than it has when it's free. But if a nucleon has less energy, Einstein tells us, and a lot less energy, it also has less mass, and that's strange, right? So the mass of a nucleus is less than the sum of the mass of its constituent nucleons. So if we take the mass of a free proton and multiply it by the number of protons, and take the mass of a free neutron, multiply it by the number of neutrons, we would expect that would be the mass of the nucleus, right? Well, it turns out that the mass of the nucleus is less than that number. And that difference there is a significant amount of energy. And this is why your mass number is not the same as the mass of a nucleus, right? That I think we mentioned that last time. This is sort of the mass number, right? How many nucleons do you have? The mass of the nucleus is a separate thing, and the difference is important because it indicates how much energy has been released in going from the state of a free protons and neutrons into a nucleus. So where did all that lost mass go? It's converted into what we call binding energy. So to rewrite that equation that we just did in Einstein's terms, the energy of the free nucleons is the mass of those nucleons times c squared. The difference between the energy of the free nucleons and the energy of the nucleus, or the mass of the nucleus rather, or the mass energy of the nucleus is the binding energy, right? So we have less mass in the nucleus, and that difference there, the difference in mass times c squared, is our binding energy. And we can write that here, where this is our number of protons times the mass of protons. This is our neutrons times the mass of neutrons. So how do we think about that binding energy? It's a strange and a hard thing to get our heads around. So let me give you one metaphor. So if we think about that binding energy as a kind of release of potential energy, that might help us. So when we're far from the nucleus, when our nucleon is far from the nucleus, it has a positive potential energy. Just like a boulder has a positive potential energy when we move it to the top of the mountain. Now, when we let that boulder roll down the mountain, that potential energy is converted into kinetic energy, into thermal and frictional energy, right? So we get a release of energy as uh, that boulder moves rolls down the mountain. When a nucleon is pulled closer to the nucleus, we get that same kind of release of energy. Its potential energy is converted into that binding energy. Um, and that binding energy is a significant amount of energy, as we'll see in just a second. This is, one metaphor for how to think about this, but there are going to be some flaws with that if we explored that too close. So let's talk about how that works in practice and why it matters. Um, and generally, your binding energy is going to be proportional to the number of nucleons, right? So if we look at our plot over here, how much binding energy do we have per nucleon? It's roughly about 8, right? But the curve in this plot matters a lot when we talk about fission and fusion, and we'll see why. If you'll notice, there's a hump here, right? So a mid-sized molecule or element has more binding energy per nucleon than either a large element or a really small element. Why is that? Well, there's a kind of interaction going on in the nucleus between two forces. We have the strong force, which is pulling those protons together, and neutrons as well, and the Coulomb force, which is pushing the protons apart. When we have a really large nucleus, the Coulomb force gets stronger relative to the strong force. Why? Because we have a whole bunch of neutrons in the way of the protons. Plus, there's just a limited amount of space, so the protons get pushed farther apart. So that strong force, which is only acts at very close distances, starts to lose some of its effect. So that's part of the reason when you get really large elemental molecules that they start to become unstable, because that Coulomb force starts to be stronger relatively than the binding force. So our binding force per nucleon is lower down here. And we can make a different but similar sort of case about the smaller molecules. So what does that have to do with fusion or fission? Well, the binding energy per nucleon is largest for those mid-sized molecules. Um, if we take two small molecules with a certain number of nucleons and we join them together, all of a sudden they're going to have a larger BE, right? Let's say we have two molecules that have 6 units of binding energy per nucleon. And we combine those into a molecule that has 8 units of binding energy per nucleon. We still have the same number of nucleons, but now we have a bunch more binding energy. And that's going to result in a release of energy. Why is fusion so difficult? Well, because we have to get those two smaller molecules together. So let's say these are our hydrogen molecules that we're trying to force together and make a helium molecule. They don't want to go next to each other, right? At distances, the Coulomb force here is going to be repulsive between those protons. And so they're going to try and push apart. So we have to throw them together at tremendous speeds in order that they get close enough that the strong force acts together. So Here, r is our distance between the molecules. Let's say we have two hydrogen molecules. Um, when they're this far away, they're going to repel each other. Um, Only when we get a certain closeness together will they start to be pulled together. So you can think of this little red line here as a hill, right? I need to throw my hydrogen molecule strong, fast enough so that it rolls up this hill, overcomes all that repulsion, and gets close enough so that the strong force can begin to act and pull it close together like that. So this plot up here gives us a sense of the kind of hill that you have to get over in order for two molecules that are both positively charged, right? They don't have, these are um, like alpha particles, essentially. They don't have any electrons. They have to overcome that Coulomb repulsion in order to be pulled together again. If that works, if they get pulled together, then they're going to have a large amount of binding energy, and it's going to release a ton of energy, and it's going to power all of our earthly desires without creating a lot of pollution. So if we could just get fusion to work, it would just be dandy. Fission works in a similar way, except it's on the flip side of that binding energy per nucleon chart. Rather than trying to, fusion tries to take like that. If you remember, that chart looks sort of like this, right? Or rather like that. Um, fusion tries to take two small molecules with low binding energy per nucleon and join them together to be mid-sized. Fission takes a large um, molecule and tries to split it so it becomes mid-sized. Um, and then that mid-sized molecule has a higher binding energy per nucleon, which results in a release of tremendous energy. We have the same kinds of problems with fission, although it's obviously been easier for us to overcome that. Because uranium is naturally unstable, we can sort of throw a particle at it and get it to split in half easier than we can get two hydrogen hydrogen nuclei to join together